This is John Whitaker for the Mathematical Analysis 2 class, and this is our 24th video lecture, and today we're going to talk about absolute convergence of series. I thought we might get to that during the last lecture, but we ended right before we got to it. We're also going to talk about the addition of series. We're also going to talk about the so-called product of series and know when that is convergent or not. Okay, so we're going to start off with the definition of absolutely convergent. So our definition is a series, and that's the sum of a sub n, is said to converge absolutely if the series, the sum of the absolute value of a sub n converges. As a theorem, if the series of a sub n converges absolutely, then the series a sub n converges. And we'll get out of the way in just a second, but I believe this proof, the proof of this statement can be done using the comparison test in one or two lines. But we're going to look at using the Cauchy criterion instead. We'll do the proof of that in just a second. Using the Cauchy criterion. So here's the proof that we'll present, and this is based on comments made about the proof from our text. But we're going to let the series of a sub n's converge absolutely. We're going to let epsilon be greater than 0 be given. Since the sum of the series of a sub n converges absolutely, then by the Cauchy criterion, there exists an n and a natural number such that for all n m bigger than or equal to this big N, the sum of the absolute value of the sum of the absolute values of the a sub n as here let's write down a sub k. As k runs from m to n, this will be less than epsilon. And let me write this down. So this will be less than epsilon, but let me translate this. Look, this is the absolute value of a sub k, so they end up being positive numbers, non-negative numbers. And when you sum them up, you get a non-negative number. And when you take the absolute value of that, you get the same number. So this is the sum of this, which we know to be less than epsilon. So those two things are the same. This thing's less than epsilon by the Cauchy criterion. Okay. Thus, for all n and m bigger than or equal to this big N, we have that the absolute value of the sum of the base of k, is k runs from m to n, is less than or equal to the sum of the absolute values of the base of k's as k runs from m to n. Now that's true by the triangle inequality, but this part is less than epsilon. So we're saying for there exists this big N such that for all m and n bigger than or equal to this big N, the absolute value of this sum is less than epsilon, but that's what it takes to show that this sum converges. So thus, by the Cauchy criterion series, the sum of the ace of k's, or ace of n, if you will, is n runs from whatever it does, converges. And that is that proof. I'd like to look at an example. So if you look at the sum as n runs from 1 to infinity of minus 1 to the n over n squared. Now this converges absolutely, and that's because the sum as n runs from 1 to infinity of minus 1 to the n over n squared, the absolute value of that, is equal to the sum as n runs from 1 to infinity of 1 over n squared, which is a convergent p-series. Okay. So that's an example of a series that converges absolutely. Okay. As a definition, not every series converges absolutely. And so what we say, if the series a sub n converges, but the series of the absolute values of a sub n diverges, we say that the series of a sub n's converge. So this is the book's terminology, non-absolutely. In calculus, we say this means that it's conditionally convergent. The a sub n is a series of a sub n. So in Cal 2, we say this phrase. Okay. Let's look at an example of that. So if we take a look, we consider the series as n runs from 1 to infinity of minus 1 to the n plus 1 over n. And the first thing I'm going to do is I'm going to note that this series, that's the value of this series, equals to the series as n runs from 1 to infinity of 1 over n, which is a divergent p-series. So what that tells me is that this series we're considering does not converge absolutely. However, if we look at the original series, we look at this series as n runs from 1, or I'll say n, this series. The absolute value minus 1, well, I should say, look at each term that we would be having in the series. So this will be minus 1 to the squared over 1. Take its absolute value. That's less than or equal to minus 1 to the third over 2, which is less than or equal to minus 1 to the fourth over 3, and so forth. Okay? So what I'm doing is checking the alternating series test conditions here. That's what we're going to use. So we have one part of the alternating series test verified. And if you look at minus 1 to the 2m minus 1 plus 1 over 2m minus 1, that is, I'm looking at the 2m minus 1 term of what we're adding up here. Okay, this is going to be greater than or equal to 0. And if you look at the 2m term, which is minus 1 to the 2m plus 1 over 2m, well, here, Brendan said this was greater than or equal to 0. This part is greater than or equal to 0. And this part right here is just minus 1 to the 2m, minus 1 to an even number is going to be a positive 1. So we've got positive divided by positive, that's what's greater than or equal to 0. Here, the 2m is an even number. When you add 1 to it, that's odd. Minus 1 to odd is minus 1. Minus 1 over this m is positive. Minus 1 over a positive number, that's going to be less than or equal to 0. And the limit as n goes to infinity of minus 1 to the n plus 1 over n, that's going to be equal to 0. So, by the alternating series test, that tells us that the series minus 1 to the n plus 1 over n, as n runs from 1 to infinity, that quantity converges. So just to write a conclusionary statement here, what this is telling us, I'll write it in just a second, is that our original problem is a series that converges non-absolutely. Let me write that up. Because this series is n runs from 1 to infinity. Minus 1 to the n plus 1 over n converges non-absolutely. Okay. The next thing we're going to do is talk about the addition of two convergent series, and how that converges. And it'll be a short, easy to prove theorem. And here's what we have. We have if the sum of a sub n's equals to a, so converges to a, and the sum of the B sub n equals to B. So that's a series that converges to B. Then the sum of the A sub n plus B sub n, that equals to A plus B. And not only that, but the sum of a constant times A sub n will be equal to C times A. So what this is saying is if you give me two convergent series, if you take the addition of the sequences involved, call that, do a series of that, it's going to converge to what the first series converges to, plus what the second series converges to. And if you give me a convergent series and multiply each one of its terms by a constant, and you add that up, then what that converges to is C times what the sum of the A sub n's is. So here's the proof. We'll let A sub n, big A sub n, be the terms involved in the sequence of partial sums, and B sub n be the terms in the sequence of partial sums for the little b sub k's here. Then A sub n plus B sub n would be equal to the sum as k runs from 0 to n of A sub k plus B sub k. That's what we can rewrite it. And that would be the partial sums, or term in the sequence of partial sums of the series, the infinite series of the A sub n plus B sub n, right here. Okay? And since the limit as n goes to infinity of A sub n equals to A, we know that because the series of the little a sub n's converge to big A. But not only can we say that about the series of the little a sub n, we can say something similarly about the series of little b sub n's. I will say that next. And the limit as n goes to infinity of the b sub n's equal to b, then the limit as n goes to infinity of A sub n plus B sub n, this is by properties of limits, that's going to be equal to A plus B. And remember, this was the limit of the partial sums for the series of the little a sub n plus B sub n. So what that tells us is the sequence of partial sums A sub n plus B sub n for the series k runs from 0 to infinity of A sub k plus B sub k converges and converges to A plus B. So this series, runs from 0 to infinity of A sub n plus B sub n converges to A plus B. Okay, we also have to deal with part of this theorem that has to do with the constant, but it's very similarly done using limits with the sequence of partial sums. So similarly, C times A sub n, which is equal to C times the sum as k runs from 0 to n of little a sub n, which equals to the sum as k runs from 0 to n of C times, this should be a sub k. C times a sub k. That means C times a sub n right here is a term in the sequence of partial sums, okay, for the series, the sum as n runs to 0 to infinity of C times a sub n. Okay? Note the limit as n goes to infinity of C times a sub n will be equal to, well, this is a constant, limit constant times something. It's just that constant times the limit of this guy, which would just be a. So writing this down now, what we have. So the sequence of partial sums, and that's C times a sub n, for the sum as n runs from 0 to infinity of C times a sub n converges to C times a, thus that means the series converges to C times a. And that's what we want to prove. So that means that theorem. Next, I want to look at a definition for the product, okay? Two series. So, given the sum as n runs from 0 to infinity of a sub n, and the series as n runs from 0 to infinity of b sub n, we put c sub n equal to the sum as k runs from 0 up to n of a sub k, b sub n minus k. And here this is where n is equal to 0, 1, 2, forever. Okay? And call the sum as n runs from 0 to infinity of the c sub n the product of the series the sum as n runs from 0 to infinity of a sub n with and the series of the b sub n's. That's its definition. Let's look at an example. Before I go to looking at the example, I want to tell you, if you took this series and just multiplied it by this series, term by term, and you said, well, maybe one way of looking at it is you'd have a sub 1 times this series plus a sub 2 times this series. That's one way of kind of thinking of it. And maybe rearranging the terms a little bit in the way that I said here, how you can multiply these out, you would get exactly this sum being the product. Okay? Rearranging the terms a little bit. Well, let's look at an example. let's consider the series. The sum is n run from 0 to infinity of minus 1 to the n over the square root of n plus 1. Okay? And I'm going to write out some of its terms. So this will be equal to 1. Then it would be minus 1 over the square root of 2. And then it would be plus 1 over the square root of 3. Then it would be minus 1 over the square root of 4. And so forth. This series converges by the alternating series test. Okay. And I'm going to verify that as, if you look at the original problem, the series is n run from 0 to infinity of minus 1 to the n over the square root of n plus 1. That can be rewritten as the sum as n runs from 1 to infinity of minus 1 to the n plus 1 over the square root of n. That's one way of rewriting it. And if you look at the absolute values of each one of these terms, so when n is equal to 1, the absolute value of minus 1, this will be squared over the square root of 1. That's going to be greater than or equal to the absolute value of minus 1 cubed over the square root of 2, and so forth, forever. So that's part of the conditions for the alternating series test. And if you look at the 2m plus 1 term, so here that would be minus 1 to the 2m plus 1 over the square root. So this would be 2m plus 1 plus 1 over the square root of 2m plus 1. Well, that's going to be greater than or equal to 0. Whereas the 2m term would be minus 1 to the 2m plus 1 over the square root of 2m, and that's going to be less than or equal to 0. That's another condition of the alternating series test that we're verifying. And then finally, we've got to take that limit. And the limit as n goes to infinity of minus 1 to the n plus 1 over the square root of n. That's going to be equal to 0. Okay. So that's the condition of the alternating series test, and when that happens, it tells us that the series converges. Now, what we want to turn to is the product of our series, which I'll rewrite as n going from 0 to infinity, minus 1 to the n over the square root of n, with itself. Okay. Is found by noting the ace of n is equal to minus 1 to the n over the square root of the n, and b sub n is equal to the same thing. Okay. So we need to look at the c sub n terms that we're going to be adding. So C sub 0, that's equal to the sum as k starts from 0 and goes to n, which in this case is 0. It was a sub k, b to the n minus k, so that's 0 minus k here. That's just going to be equal to a sub 0, b sub 0. And in this case, that is, it's 1 over the square root of, I made a mistake in what I worked on the product. I made a mistake. Let's go back. I made a mistake in my notation here. So here, this is the square root of n plus 1, okay? When we start from 0. And so this should be over the square root of n plus 1, n plus 1 here, okay? So please make those changes. I made a mistake. Now we're going back to compute those c sub n's. And this is going to be the square root of 1 times the square root of 1, which is just equal to 1. C sub 1 is equal to the sum as k runs from 0 to 1 of a sub k, b sub 1 minus k, which is going to be equal to, well, it's going to be a sub 0, b sub 1 plus, it's going to be a sub 1, b sub 0, which is going to be equal to 1 over the square root of 1, and then times the b sub 1 is going to be minus 1, b sub 1 minus 1 over the square root of 2, plus, here the a sub 1 is going to be minus 1 over the square root of 2, and then this is going to be b sub 0 is 1 over the square root of 1. And so what we end up getting there is minus 1 over the square root of 2 plus 1 over the square root of 2. C sub 2 is going to be equal to the sum as k runs from 0 to 2 of a sub k, b sub 2 minus k. What I'm trying to do here is get some experience of computing these c's. And so that's equal to a sub 0, b sub 2 plus a sub 1, b sub 1 plus a sub 2, b sub 0, which is going to be equal to 1 over the square root of 1 times, this is going to be 1, over the square root of, I think, 3. And then plus here, this is going to be minus 1 over the square root of 2. And here, this is going to be minus 1 over the square root of 2. And then this is plus 1 over the square root of 3. I'm just going to leave it like that. We'll also do C sub 3 just to get some more experience working, calculating these. So C sub 3 is equal to a sub 0, b sub 3 plus a sub 1, b sub 2 plus, it's going to be a sub 2, b sub 1 plus a sub 3, b sub 0. And that's going to be equal to, okay, so it's going to be 1, and then b sub 3 is going to be minus 1 over the square root of 4 plus a sub 1 is minus 1 over the square root of 2, and b sub 2 is going to be 1 over the square root of 3. A sub 2 is going to be 1 over the square root of 3. And b sub 1 is going to be minus 1 over the square root of 2. And a sub 3, that's going to be, I think it's 1, no, it's minus 1 over the square root of 4. And then b sub 0 is just 1. And that's equal to, if you want, it's minus, and it'd be 1 over the square root of 4 plus 1 over the square root of 2 times square root of 3. Plus, again, the same thing, 1 square root of 3 times square root of 2 plus 1 over the square root of 4. So in general, the product of n running from 0 to infinity of minus 1 to the n over the square root of n plus 1 with itself is, well, it's the sum as n runs from 0 to infinity of the c sub n, which equals to, well, it was 1, and then it was minus 1 over the square root of 2. I think it says plus 1 over the square root of 2. No, I think it was just 1 over the square root of 2 plus 1 over the square root of 2. And then plus, it's 1 over the square root of 3 plus 1 over the square root of 2 times square root of 2. And then plus 1 over the square root of 3. And then I'm going to write down this last term. It was minus what we just got here. It's 1 over the square root of 4 plus 1 over the square root of 2 times square root of 3 plus 1 over the square root of 3. So it's the same thing. That's square root of 2. And then it's plus 1/4. And it keeps going. But we can rewrite that nicely. Let's just get those terms down. Really, just following the form, the generic form, here's what we get. I'm sorry, I should give you more time to look at that. Let me leave it. All right. So it goes on forever. Well, first of all, and c sub m is equal to this sum as k runs from 0 to n of a sub k times b to the n minus k. I guess it's this form that I wanted to look at more, which is really equal to for our problem is the sum as k runs from 0 to n. The a sub k is minus 1 to the k over the square root of k plus 1. And the b sub n minus k will be minus 1 to the n minus k over the square root of n minus k plus 1. And that ends up being minus 1 to the n. So I'll take that out of the summation here. Sum as k runs from 0 to n. And here we have 1 over the square root, rewriting them in different order. N minus k plus 1 times 1 over the square root of k plus 1. That's what we have. All right, let's look at something. Let's make an observation here about the denominator without the square root. Here's what I want you to notice. You can do this. It's just algebra here. If you make this observation that n minus k plus 1 times k plus 1 is the same thing as n over 2 plus 1 to b squared minus n over 2 minus k to b squared. Okay, you can multiply these out, you get that they're exactly the same, which is less than or equal to just this guy. Okay, because we wouldn't be taking away some positive number from it, a non-negative number. Okay? Then here's what we get based on that algebraic observation. what we get is 1 over n over 2 plus 1 to be squared is going to be less than or equal to 1 over n minus k plus 1 times k plus 1. And so, that's going to give us that 1 over n over 2 plus 1, take the square root since both of these guys are positive, is going to be less than or equal to, and the square root is increasing. The square root of n minus k plus 1 times the square root of k plus 1. So, that tells me that 2 over n plus 2 is less than or equal to 1 over the square root of n minus k plus 1 times the square root of k plus 1. That's what we are. And it turns out, I think you can even say it here, by the comparison test, this guy's going to, well, first of all, this guy's going to diverge, and this is bigger, so it's going to force this to diverge. Okay? So the sum of these guys to diverge. But I'm going to do it a different way. Okay? I'm going to say, thus, the absolute values of the c sub n, which is the absolute value minus 1 to the n times the sum as n runs, or k runs, from 0 to n of 1 over the square root of n minus k plus 1 times the square root of k plus 1, which work with it. That's going to be equal to the absolute value of the sum as k runs from 0 to n of 1 over the square root of n minus k plus 1 times the square root of k plus 1. Of course, these are all positive terms, so the absolute value of them are just the cells. That's the sum as k runs from 0 to n of 1 over the square root of n minus k plus 1 times the square root of k plus 1. And that's going to be bigger than or equal to the sum of 2 over n plus 2, which equals to 2 over n plus 2 times n plus 1. So that's what that sum is. This is as k runs from 0 to n. There's n plus 1 terms. We're adding up the constant with respect to k. That's what we get. Since the limit as n goes to infinity of 2 times n plus 1 over n plus 2 equals to 2, you can do that by L'Hopital's rule, then the limit as n goes to infinity of c sub n, the absolute value of that, can't be 0, because it's got to be bigger than this. So that tells us that the limit as n goes to infinity of the c sub n can't be 0. And so the sum of the c sub n's as n runs from 0 to infinity diverges by the divergence test. And this is a way of doing it, doing this problem, but I also want to tell you you could use the comparison test and got it a little bit quicker. I'd like to write up what we just saw here, what we're noting about this example. So what we just observed So, this was an example of the product of two convergent series divergent. Okay? Okay? And so what we would like to do is give some kind of theorem that would enable that if in some way, that would give us some kind of a way of judging when the product is going to be convergent. And so that's what I'm going to write up next. Okay? So this theorem has a good bit of supposition to it. It says, suppose, first of all, that the series as n run from 0 to infinity of a sub n converges absolutely. B, that the series as n runs from 0 to infinity of a sub n equals to a. So if it converges absolutely, then the original series converges. We're going to say it goes to a. We're going to assume that the series of the b sub n's, they converge to b, and a fourth criteria in substitution is that the c sub n's are equal to the sum as k runs from 0 to n of a sub k, b sub n minus k. And this is, we're defining this for n equaling 0, 1, 2, 3, forever. Then, the product, so that's as n runs from 0 to infinity of the c sub n's, product series, converges. That's what we have. And not only it converges, but it converges to a times b. So it converges to the product of each of the series. The proof is next, and it's algebraically messy. Okay? But it's more computational than anything else. But anyway, it's a little messy. Here it is. Proof, we let, it's very messy symbolic. We let a sub n equal to the a term, we're defining the term of the, and the sequence of partial sums for the little a sub k. B sub n to be equal to a term in the partial sum, genetic term in the partial sum, for the series of the little b sub n's. I'm going to say script c sub k to be equal to the term c sub n here of the partial sums for the product series. Here, this should have been k. Make that change. And I'm going to define beta sub n. Okay, that's a beta. It's got a tail when it's b. To be equal to b sub n minus b. That's what we're going to do. Then, here's what the script c sub n is going to be looking like. It looks like c sub 0 plus c sub 1 plus c sub 2 plus all the way up to c sub n. And that's what it is. That. Now, what's these guys? Well, this can be expanded to be equal to a sub 0, b sub 0 plus a sub 0, b sub 1 plus a sub 1 b sub 0, that was c sub 1, plus c sub 2 is a sub 0 b sub 2 plus a sub 1 b sub 1 plus a sub 2 b sub 0. Okay. And then we keep going, and the c sub n term is a sub 0 b sub n plus a sub 1 b sub n minus 1 plus a sub 2 b sub n minus 2 plus, and you keep going all the way up to the last one is a sub n b sub 0. And I would like to include the previous to the last one. So a sub n minus 1 b sub 1 plus a sub n b sub 0. Now, what we'll say is this is equal to, well, a sub 0, and this one, and this one, okay? It's in all of them. And so you pull out a sub 0, and what you're left with is little b sub 0 plus little b sub 1, all the way up to b sub n, and that is big B sub n. Plus, and do something similarly, a sub 1 will be times big B sub n minus 1, plus a sub 2 times big B sub n minus 2, all the way, you keep going, up to a sub n b sub 0. And then by what we've written here about the b sub n, that could be beta sub n plus b, and that's what I'm going to stick in to replace the b, so whatever, from what we've just written. Okay, so as I said, that's going to be a sub 0 times b plus beta sub n plus a sub 1 times b plus beta sub n minus 1 plus a sub 2 b plus beta sub n minus 2 plus, we'll keep going, all the way up to a sub n, and then this would be b plus beta, that's a beta, sub 0. That's what we get. Okay, this can be rewritten as a sub n times b. So b's in every one of them, it's a sub n times b. So b's in this one times a sub 0, b's in this one times a sub 1, b's in this one times a sub 2. You take out the b, and then a sub 0 plus a sub 1 plus a sub 2, all the way up to little a sub n. That's big A sub n. Okay? And then plus a sub 0 times beta sub n plus a sub 1 times beta sub n minus 1 plus a sub 2 times beta sub n minus 2, plus you keep going all the way up to a sub n times beta sub 0. That's these guys being involved. A sub 2. And I have to write all that out. Okay. So to simplify this part notationally, what we're going to say is we're going to let gamma sub n be equal to a sub 0 beta sub n plus a sub 1 beta sub n minus 1 plus all the way up to a sub n beta sub 0. Now, remember, this was equal to the C sub n, the strict C sub n, the partial sums for the product series. So that's what this was equal to. And what we want to do for the theorem is we want to show that the sequence of partial sums for that product series converges to a big A times big B. So let me write that down. We want to show this, but to show the limit as n goes to infinity of the script C sub n is equal to A times B, okay? Well, we have to show that this guy right here goes to A times B as n goes to 50. But this part does go to A times B as n goes to 50. So this part must go to 0. And that's what I'm going to indicate here. We only need to show that the limit as n goes to infinity of gamma sub n equals to 0 as the limit as n goes to infinity of A sub n b equals to A times b. Okay, so that's the remainder of the proof is to show that the limit as n goes to infinity of gamma sub n equals to 0. But there's more notation coming. We still got a little ways to go, but not a lot. So we're going to put alpha equal to the sum as n run from 0 to infinity of the A sub n. We know that alpha exists. Because in our assumption of this theorem, the A sub n's converge absolutely. Now what we're going to do is we're going to let epsilon be greater than 0 be given. Okay. Since the limit as n goes to infinity of B sub n, okay, equals to B, then the limit as n goes to infinity of the theta sub n, because of the way they're defined, that has to be equal to 0. Hence, we can choose a natural number n such that the absolute value of beta sub n will be less than epsilon, because this limit, for all little n's bigger than or equal to this big N. Okay. Now, for every n greater than or equal to big N, gamma sub n, which equals to, just a reminder, it's A sub 0, beta sub n plus, well, I'm going to expand this. Let me write it down here. Gamma sub n is equal to this. It's A sub 0, beta sub n, plus A sub 1, beta sub n minus 1. Plus, you keep going, you get to some point A sub n minus big N minus 1, beta sub big N minus 1, that'll be plus 1. Plus 1 is what it should be. You know, these indices always add up to little n. Plus, the next one is A sub n minus big N times beta sub big N plus a sub n minus n plus 1 times beta sub big N minus 1. And then you keep going. And then the last term you get is a sub n beta sub 0. So that's what gamma sub n is. So for all n bigger than or equal to big N, we've got that absolute value of gamma sub n is going to be less than or equal to, well, I'm going to say the absolute value of this first part here. So up to this term. So here I'm going to have alpha sub 0, beta sub n, plus alpha sub 1, beta sub n minus 1, plus all the way up to here, this term. So it's a sub n minus 1, beta sub n plus 1, plus, so I'm using the triangle inequality. Here it would be the absolute value of a sub n minus n, beta sub n, okay, plus a sub little n minus big N plus 1, beta sub big N minus 1, plus, keep going, all the way up to a sub n, beta sub 0. Okay. Using the triangle inequality, we'll get that this is less than or equal to alpha, a sub 0 is absolute value, and b beta sub n plus a sub 1's absolute value times beta sub n minus 1 plus, and keep going all the way up to a sub n minus 1 times, both these are exact absolute values, beta sub n plus 1, plus this other string, which I won't break up. And so this is a sub n minus n, beta sub n, plus a sub n minus big N plus 1, beta sub big N minus 1, plus all the way up to a sub n beta sub 0. Okay. Now, each one of these terms, and that's why we're breaking them up in this way, is going to be less than epsilon. So I'm going to replace each one of these terms with epsilon. So it's the absolute value of a sub 0 times epsilon plus absolute value of a sub 1 times epsilon plus the absolute value of a sub n minus big N minus 1 times epsilon. And then the rest of this guy I'm going to leave as is. It's a sub n minus n, beta sub n plus a sub n minus n plus 1, beta sub n minus 1 plus a sub n beta sub 0, which I'll rewrite as being equal to epsilon times the sum as k runs from 0 up to n minus big N minus 1 of the absolute value of a sub k, and then plus this term here. So this is a sub n minus n beta sub n plus a sub n minus n plus 1 beta sub n minus 1 plus a sub n beta sub 0. That's the values. And this guy right here is going to be less than alpha. Excuse me. So I'm going to make that replacement. Remember, alpha is what the whole series converges to, the absolute value of the a sub k's or a sub n's converge to. Okay, we're getting close to the finish now. So this is less than or equal to epsilon times alpha plus the a sub n minus big N, b sub n plus a sub n minus n plus 1, beta sub n minus 1, all the way up to a sub n beta sub 0. And now what we're going to do is we're going to keep n, big N fixed and let little n go to infinity. So keeping big N fixed and letting little n go to infinity. We have, so the lim sup as n goes to infinity of the absolute value of the gamma sub n's will be less than or equal to the lim sup as n goes to infinity of this quantity is epsilon times alpha plus the a sub n minus n b sub n plus a sub n minus big N plus 1 beta sub n minus 1 plus all the way up to little a sub n beta sub 0. Okay. Which is less than or equal to, here, this is the lim sup as n goes to infinity of epsilon times alpha plus the lim sup as n goes to infinity of, well, the absolute value of a sub n minus n times the absolute value of beta sub n plus absolute value of a sub n minus big N plus 1 of the absolute value of b sub n minus 1 plus all the way up to plus the absolute value of a sub n times the absolute value of b sub 0. But what we're going to get there is equal to epsilon times alpha plus 0 as the limit as n goes, say it's k, goes to infinity of the absolute value of a sub k. That has to be equal to 0. And the reason that that has to be equal to 0 is because this series converges. So by the divergence test, this thing has to go to 0. Okay? Otherwise, this series could not converge, which we're assuming it's the sum of the a sub n's absolute convergent. Okay. Thus, what we have is that 0 is less than or equal to the lim sup of gamma sub n, which is going to be less than or equal to epsilon times alpha. Since epsilon is an arbitrary positive number, that means that the lim sup of the gamma sub n has to equal 0, and that proves. That means that the limit as n goes to infinity, this infinity, of the absolute value of gamma sub n equals to 0. And so that says that the limit as n goes to infinity of gamma sub n equals to 0. And that's what we needed to show in that conclusion. I'm sorry for so long. Thank you very much for your time and patience.